Hello everyone, this video is just a talk through of the paper 1, the physical geography exam. On the first slide here, you can just see a brief overview then and a reminder of the topics that you're going to be asked questions on. So in paper 1, it's obviously natural hazards, you've got the living world, and then you've got physical landscapes. Just a brief reminder whilst we're here that in the living world section, you're obviously going to choose to answer on cold environments and not deserts because we haven't studied these. And the same reminder for the physical landscape section. So you're going to answer about coasts and rivers and not the questions then on glacial landscapes. Again, we haven't studied those. So at the bottom here, I've just put in that little screenshot. You'll see this on the paper anyway, but just to remind you that you're going to answer questions 3 and 4. Okay, it does tell you this in the paper, so just make sure you check it and have a little look over it before you start attempting questions in that section. So if we start at the beginning then, the first section you'll see when you open the paper is the challenges of natural hazards. So within natural hazards, the first thing you need to be reminded of is exactly what a natural hazard is. So a natural hazard, as it says here, is a natural process that can cause death, injury or disruption to humans, property or possessions. And so you can group your types of hazards into things like tectonic, for example, so to do with the plates, which we'll talk about in a minute. You could group them into geology, and you could call them geological hazards. You might go and group them in terms of weather, and you might call them atmospheric hazards. So just check that you're able to at least think of an example for each one of these. So for tectonic, for example, I might put earthquakes. For geological, I might put things like landslides. Atmospheric, I might put things like hurricanes. So you might be asked to give an example of one of these for 1 mark. So just check you can do at least one of each. So if we go and zoom in a little bit more on tectonic hazards, it's important you understand the different layers that we have within the earth and what each of these layers is like. So if we look at this diagram, the layer in which we live on is called the crust. Beneath that, you've got your mantle, then it's your outer core, and right in the centre of the earth then is the inner core. So if I look at the ideal conditions within the crust, I can see that the crust varies in thickness. It's about 5 to 10 kilometres beneath the ocean, made up of several large tectonic plates, and it's those tectonic plates that cause us the things like earthquakes and volcanoes. We'll talk about those in a minute. The mantle here is the widest layer. So it's about 2,900 kilometres thick. So lots of heat and pressure here means that this rock is often liquid, and this leads us to our convection currents. We'll talk about convection currents very shortly. Then right in the centre of the earth is your inner and outer core. So the hottest section, it's about 5,000 degrees, pretty dense rock. It's 4 times denser there than it is on the crust. So again, just check. Do you know the differences between each one of these layers? And if you were asked in the exam, would you have a sentence to say about each? So if we think about convection currents then, first thing we have to know to have convection currents is that radioactive decay then of some of the elements in the core are going to generate us a lot of heat. Okay, that heat then has to go somewhere. So then what happens with that heat is that it starts to obviously heat up the rock that's above it, so the magma. It becomes less dense, and as with everything warm, it's going to rise. As these convection currents move towards the top, so close to the surface of the earth, they become even denser and then start to slowly sink. This is going to generate us a nice circular movement, and this helps to create some drag on the base of the tectonic plate. So really think of it like a conveyor belt. It's going to warm, it's going to start to rise, it cools and spreads, so it sinks back down. And on top of this up here is where we have our volcanoes, for example, living on the surface. So it's being dragged along by those convection currents. So there are 3 types of plate boundary that you'll need to know for the exam. So let's just go through each one of these. So the top one here that you can see is a destructive plate margin. It's destructive here because the crust is being destroyed. So if I have a little look at this picture here, I've got one tectonic plate that's been subducted, so dragged down beneath the other one. So So what's going to happen is I'm going to get lots of friction. So the friction is going to occur at this point here, which is going to cause me to get an earthquake. This plate here is going to be melted down. So it's going to give me a nice big pool of magma down here beneath the surface, which is going to force its way to the top. But that's what's going to cause us, yes, some more earthquakes, but also it's going to cool and condense and form us some volcanoes. So that's what's happening at a destructive margin. The next one we have is a constructive margin. So completely opposite. If you're at a constructive margin, you're creating new crust. So here I've got two tectonic plates that are pulling apart or moving away from each other. And this magma is rising in the gap between them, cooling and condensing. And that again is going to form me some nice big volcanoes. I can still get some earthquakes here as well. Just bear that in mind. This transition where we've got the plates pulling apart is never going to be smooth. So I'd expect to see some small earthquakes here. And last but not least then at the bottom is a conservative plate margin. So a conservative plate margin is when you've got two tectonic plates that are sliding past each other. Now, it doesn't always have to be in opposite directions. It can go in the same direction but at different speeds. Just bear in mind that these rock surfaces here aren't smooth, so they're going to get stuck. That pressure and that energy is going to build up, so we're going to see lots of strain energy here. And then all of a sudden it will get released, and it's when that pressure gets released, that's what causes us to have an earthquake. So if we think more about earthquakes, as we said, this pressure or strain energy is going to build up where these two tectonic plates are. But there are some key terms here that are worth noting. So if we start then with a focus, so the focus is the point where the energy is initially released. The epicenter is the point directly above that on the surface of the earth. And then when that energy starts to radiate outwards, those are what we call our seismic waves. So if we think about how we might go about managing an earthquake, there's not really too much we can do in terms of prevention. We can't stop earthquakes, but we can make some small adjustments to make living with them perhaps slightly easier and therefore try and reduce some of that damage. So earthquake resistant buildings, try and increase the awareness of the public and give them a bit of education, trying to increase the way we predict them and the accuracy of that. That's all going to help to prevent some of those risks of the hazard. In terms of what we can do to predict, we might use things like satellite surveying, seismometers. We might look at records to try and work out what interval these are happening. Any of those. They might ask you to outline one or two of these ways in the exam. So just check now. If you need to pause, please do. But just check you'd be able to talk about some of these ideas. So you have two earthquake case studies. So these are normally what might form a 9 or a 6 marker. Okay, so to put a little reminder there. Just check, again, you understand the purpose of each of these case studies. So your LIC case study is the Gorka earthquake in Nepal in 2015. So that's your 7.8 magnitude one. This is the one here that caused the landslide as well. So you haven't just got the earthquake to talk about, it's the landslide, that secondary impact as well to draw on. Think about the amount of people here that unfortunately have lost their life, because you'll be able to compare that in a minute to Tohoku. So think about which one of these perhaps has got the worst effects. Think about the management as well. I think that fact over here about aid is particularly important and gives you lots to talk about. If I compare that then to the Tohoku earthquake in Japan in 2011, so this is your 9 magnitude earthquake. It's the 4th largest one that you've got on record. Again, just go back and check some of these impacts that we picked out before. So 20 people injured when the roof collapsed on a graduation ceremony. Within 6 days of this earthquake, they'd rebuilt most of the roads around this area. So you could argue that perhaps they've responded slightly better to this earthquake. You've got this fact over here about dead, unfortunately buried in mass graves to sort of reduce the spread of disease. Think about what impact that has socially. Look at the amount of people here that are reached with aid and emergency supplies. Why is that particularly good? So all of these effects you'd want to evaluate in that 9 marker. So they might ask you to evaluate whether you think primary or secondary effects were worse. They might ask you to evaluate whether you think short-term or long-term responses were better. So again, just pause now if you need to, but check, do you understand what a primary effect is? So something that happens straight away. Do you understand what an immediate versus a long-term response is? I'd go into that exam with just a brief idea in my mind of who I think's responded to it better and who's potentially had the worst impacts. So I've already got something in my mind that I can write about should that question come up. And briefly then, you've got a little bit on volcanic hazards just to remind you. So you don't need volcano case studies because you're doing earthquakes, but just check again. Do you understand what the ash cloud is? Do you understand what a lahar is, so that fast flowing mud? Do you know what pyroclastic flow is, that superheated gas, for example? Would you be able to pick out one or two of these in the exam and explain them? Then obviously, would you be able to manage these hazards? Sometimes they might ask you why some HICs might respond better to LICs. And just think about, well, what's the big differences between the two? If you're wealthier, what does that mean that you can do? If you've got better prediction or preparation, does that mean you're able to respond better? Would you have monitoring techniques? Would you be able to recognise some of the warning signs? Think about why people might also still continue to live in these areas. These areas, remember, are particularly beneficial for farming. The soil's of great quality. Perhaps the land in these areas is cheaper. Perhaps there's huge benefits for tourism, and that's why people continue to live in these areas. Perhaps they've lived there for their whole life. Again, are you able to explain some of those points in the exam should that question come up? And then obviously on the other side of the hazards topic is your atmospheric hazards. So just check that you're able to understand and you can explain global atmospheric circulation. Check you understand the way in which these cells work. So you have 3 cells as a reminder. You've got the Hadley cell, the Ferrel cell and the polar cell. So this diagram here really is like a mirror image. So again, just check, can you explain what's going on here for 1/4 of this diagram? Because if you can do that, then it's translated around this diagram here 4 times in theory. Think about what's happening here at the equator. So your lovely sun here is obviously going to be heating this ground. So this area is going to rise, it's going to start to spread, cools and sinks, heated back up again on the Earth's surface, so it'll rise again. Again, just recap what's happening with your pressure systems. So if you're in low pressure, it's often going to be caused by hot air rising, so we're going to expect lots of stormy, cloudy weather. High pressure, so when you've got your cold air sinking, so it's going to create this clear, calm weather. My top tip and my little slogan to remember is that winds always blow from high to low. So just remember that when you go in to explain that diagram in the exam. Tropical storms, onto the exciting stuff. Again, remember with tropical storms, they've got different names depending on which part of the world they're in. So just check now that you understand that even though it's got 3 names, it's essentially very similar. To get a tropical storm forming, you'll see here I've put in 6 clear steps for those. So if you need to pause this now to take notes or just to remind yourself, please do. The first thing that's going to happen is that the sun's going to heat this large area of the ocean. So it's going to give lots of warm and moist air. If I've got a temperature of 27 degrees, it's going to create low pressure. This is going to cause air to be sort of sucked in because I'll have a nice big thunderstorm. The trade winds will blow in the opposite direction. So that Coriolis effect, those curved winds, will start to spin this massive air, my tropical storm. The tropical storm will spin faster, so it will gather speed, normally faster than 74 miles an hour. Then it will start to gain more power, so more cool air will sink in the centre of the storm. So in the centre, the eye of my storm, have clear, calm conditions. Once this hits land, it will lose its energy source because it won't have the water anymore, and effectively will just run out of energy. So this is when we start to see all the damage and all those effects I'm sure you've seen in the pictures online. Think about what might happen to tropical storms now that we've got global warming. So if I have an increase in ocean temperatures, perhaps I'm going to see an increase in frequency of tropical storms. Think generically about how these can be managed. So obviously aid, planning, prediction, educating people on what to do. Would you be able to talk through a couple of those ideas? Again, pause it here if you need to. And then obviously, could you pick out some primary and secondary effects of a tropical storm? So things like intense winds might damage buildings, high seas and flooding, people might be left homeless, crops are damaged. And then you can obviously apply this to a case study. So the case study we've done is Typhoon Haiyan. So this is the one that happened in 2013. It's a category 5 on the Saffir-Simpson scale, so it's classed as a super typhoon. Here you've got 6,500 people that have lost their lives, 130,000 homes destroyed. In terms of management, you've got £190 million in aid that was issued. Education on typhoon preparedness was one long-term bit of aid they tried to provide. Again, way up are primary and secondary effects, which one's worse? Or short-term or long-term management better? And why do you think that? The last bit of atmospheric hazards asks you to think about climate change and think about what evidence you have for climate change in recent years. I've popped in just some of my ideas here for you to have a little look at. But in global temperatures, we've got 0.6 degrees rise since 1950. Ice sheets and glaciers, well, the Arctic sea ice has declined by 10% in the last 30 years. Sea levels risen by about 10 to 20 centimetres in the past 100 years. So again, all really 3 strong bits of evidence for climate change. They might ask you to provide one of those for 1 mark in the exam. We've also got evidence of natural change, so things that humans don't have much control over. So we've got orbital changes, sunspots, volcanic eruptions. Volcanic eruptions, I think, is probably the most memorable one. They're obviously going to contain lots of gases, they block out sunlight. Again, that's obviously going to cause an impact. In terms of what we can do to manage climate change, we've got carbon capture technology. We can plant trees then to try and absorb some of this carbon from the atmosphere. You've got international agreements. Your best example of that happened recently. So I think COP26 here for international agreements. Use of renewable energy. Think about where you are in Reading and what they're trying to do. So you've got a really good example here with Green Park, for example, and the new sustainable development that's been built there. And obviously your case study of UK weather becoming more extreme is going to be Cumbrian floods. So that's the one that had record heavy rainfall for 36 hours. It was about a month's worth of rainfall. It's caused 1,500 homes to be flooded. You've got lots of trees that have washed away. In terms of management, they've built brand new embankments. They've got some floodplain zoning and some new flood warnings. They're working with the Environment Agency. Let me have that one on. That's what EA stands for, Environment Agency, now, to provide those flood warnings. In theory, they should be better equipped if should this event happen again. Right then, now we're on to the living world topic. So this would be section B on paper 1. I've put this lovely diagram here on the first page just to remind you about where the different biomes are found in the world. Again, just check for a couple of these you're able to explain what the average conditions might be like or where they're found in the world. I suggest the most important one you definitely double check you can do that for is the tropical rainforest, which is shown in that green colour. Again, just check, well, where can you describe them as roughly being in the world? What are their climate conditions like? You might be asked to outline that in the exam. So if we go right back to basics and we think about the components of an ecosystem, you have 2 main components, your abiotic and your biotic. Abiotic is obviously non-living, biotic are living. You've got flora and fauna, so flora would be plants, fauna is animals, and these all interact with each other. So food webs and food chains show this off really nicely. The diagram you can see on the screen is obviously of a food web. Think about what might happen if one animal or plant is taken out of this, what could happen to those further down. Remember, you're probably going to have maximum of 4 or 5 links in the food chain. Well, why is that going to happen? Well, you're going to gradually lose energy as you go through this chain. Remember, animals are constantly moving, so you're going to lose energy through things like respiration, excretion, mating. Okay, so that's why all of that energy is passed on. They're quite fond of asking that question. Remember your nutrient cycle and what you've got happening here. The easiest way I think to explain this is to start at the biomass layer. So the biomass layer here, think about plants, so your trees. Think about what happens to that tree in the autumn. So it starts to lose its leaves. So it goes through the littering phase. At the litter stage on this diagram, I've now got all of my leaves on the floor. I'm getting lots of rainfall, so they're going to start to mulch down a little bit. I'll lose some of the nutrients through surface runoff when I've got that water sat on the surface of the earth. But some of those nutrients will then start to decompose, so it returns to the soil, ready to be taken up by the roots of my trees all over again, and that process continues. It's a cycle. Okay, I've got inputs, so weathering and rainfall, but I've also got outputs, so leaching and surface runoff. Again, just rewind that bit if you want to hear it explained twice, but make sure you're able to explain what happens in the nutrient cycle. If we think about this tropical rainforest biome, here's an interesting fact. So tropical rainforests cover 2% of the Earth's surface, yet they're home to over half of the world's plant and animals. Well, that's why they're particularly valuable then to protect. Interdependence. Remember, interdependence is when you've got two or more limbs that are mutually relying on each other. So think about what might happen again if we go back to that food web and food chain if one of those was taken away. Are you able to explain again, as we said on the first bit, exactly where these are found in the world? Think about where are they? So they're centred along the equator. The climate then. Can you talk about climate graphs? On a climate graph, you'd have the months across the bottom. On your left-hand side, you might have average rainfall, which would be the bars on this graph. On the right-hand side is your average temperature, which is the line. Again, in the exam, would you be able to read off what the temperature was? They might ask you to plot a bar to say this is what the precipitation was in this month, complete the graph. Again, normally temperatures are about 32 degrees. Evening is about 22 degrees. You can expect to see lots of showers, aren't you, if you're in the rainforest? So just to remind you about your layers of the rainforest, at the bottom is your shrub layer or forest floor, then it's your under canopy, then obviously your canopy, and then your emergence. If you're in the emergent layer, you've got trees of about 50 metres. Canopy beneath that gets about 70% of the sunlight. Under canopy, trees are about 20 metres high. And then forest floor is where you've got your small trees and your shrubs, etc. Your case study then of a UK ecosystem is going to be Epping Forest. Could you explain the nutrient cycle linking it into Epping Forest? So that example I did of trees in the autumn, for example, would work really well here. Think about what you've got in terms of why is this area particularly interesting, why does it need protecting? So it's a site of special scientific interest, so it's a triple SI site. Again, it's hugely valuable, so they've got lots of conservation in time. Think about how it's being managing, so think about what they're doing to encourage new growth, so they're constantly trimming things back. They're trying to maximise photosynthesis in the summer. In the winter, bacteria are going to decompose lots of that leaf litter. So these points here, or these components that I've put in, would help you to explain that nutrient cycle in action. Your case study of a tropical rainforest is going to be Indonesia. Again, can you explain a couple of plant and animal adaptations? Those are all here. So think about your drip tip leaves. They've got that waxy surface, they're funneled at the end. They allow that water to run off and drop onto the forest floor. You've got lianas that climb the trees in order to reach sunlight. Orangutans, so they've got large arms to swing in the tree canopy, so therefore they're able to get away from predators quite quickly. You've obviously got big threats in terms of deforestation. So I'm not going to read all of these to you, so pause here if you need to. But check, can you categorise these into human and physical? Think about social, economic and environmental. Could you break these down a little bit further? Again, this is a popular 6 marker here, so just check you're able to explain these. Sustainability. Think about ecotourism, that's big and on the rise at the moment. So that's tourism that promotes environment and conservation, normally pretty small scale, employs local people, educates local people about the value of the rainforest. Think about selective logging, only taking trees out when they reach a particular height, so therefore you're still left with an abundant population. And then your cold environment case study, this is normally a 9 marker, but think about opportunity versus challenge here. What are the benefits of being in a cold environment? Well, you've got huge opportunities in terms of fishing, mineral extraction, energy and tourism. But your challenges obviously are coping with the extreme temperature, its inaccessibility, buildings and infrastructure. So just check now, could you explain those opportunities and challenges? If you need to pause here, please do, but I've added all my thoughts there on the screen for you. And so last but not least, the final section then that you've got on paper 1 is the physical landscapes in the UK. So you're going to be answering questions as a reminder on coasts and rivers. So I've put this here first because remember this is a buy one get one free. Once you've learned it for coasts, you can use exactly the same processes in rivers. But to remind you, you've got 4 types of erosion, you've got 4 types of transportation. Remember in coast you're also going to have longshore drift as a process of transportation, that zigzag movement of sediment. Again, check that you're able to explain them. I would say the most 2 important ones in terms of erosion are these ones at the bottom. The abrasion and the hydraulic action, they're the ones that sort of pack the most punch if you like. Again, avoid using words in the exam like erosion. Which process are you talking about? Be really specific with the examiner. Okay, show off the fact that you know the key terms and you know what that process involves. Mechanical weathering, so think about freeze-fall weathering. This happens when water gets into the cracks in the rocks, freezes overnight, so therefore it expands and shatters the rock. Waves as well, it's really important you understand waves. So waves are created when the wind blows over the surface of the sea. So it's going to create loads of friction, it's going to produce swell in the water, and that's what causes our waves. You have 2 types of waves as a reminder. These diagrams down here show that off quite nicely. You've got constructive waves that help to build up the beach, so the swash is stronger than the backwash. Destructive waves help to remove that sediment, so therefore the backwash is a lot stronger than the swash. Your erosional landforms are what these 2 diagrams here are showing you. Let's put that title in. So you've got things like headlands and bays, you've got caves, arches, stacks and stumps. You could also talk about wave cut platforms here, but I popped in a short explanation of how these are happening. So if I've got headlands and bays, well, the waves are going to attack the coastline. The softer rock isn't going to be able to put up that much of a fight, so it's going to retreat inland. This leaves me my more resistant rock sticking out to sea, and that's my headland. Remember that headland is still going to be eroded. It's probably more vulnerable to erosion if it's left sticking out to sea. If I've got headlands and bays, then that headland in time might turn into caves, arches, stacks and stumps. Remember your case study here would be Old Harry's rocks. So hydraulic action is going to help to widen that crack over time. That will turn into a cave. Remember that cave is attacked on both sides of the headland, so eventually it will break through and form an arch. Highly likely I'm going to get freeze-fall weathering on the top of that arch, so that's going to crumble and drop into the sea and leaves me with a stack. Then I've got spits, that's a depositional landform, so I've got to have longshore drift here, that zigzag movement of sediment that we've talked about already. It's going to continue to push that sediment down the beach. Then what's going to happen is it's going to obviously be dropped due to deposition. It might extend over the river estuary. Prevailing wind and the current from the river are going to start to curve the end of that spit, which is going to create a nice sheltered area behind it. So I'm going to get lots of deposition and a salt marsh forming. My case study of a spit is going to be Spurn-Head on the Holderness coast. If I think about coastal management, I've got 2 types of coastal management. I've got hard and soft engineering. Hard engineering is typically man-made, it's a bit more intrusive, very expensive. Soft engineering in theory is natural. Your case study of Pevensey Bay has done a lot of work on beach nourishment. So building beaches up with sand to try and protect the bottom of those cliffs. That's particularly good, it's cheap, looks nice for tourists. However, if you've got a big storm, it's going to need replacing and redoing. So you might argue it's going to cost you a little bit more in the long run. You've also got some work at Pevensey Bay with groins to try and prevent longshore drift and trap that material. Still leaves the beach accessible, but what you might see is no deposition further down the coast. So it might leave some more cliffs a little bit more vulnerable to erosion further along the coast. Worth bearing in mind. For rivers then, I've broken this down into upper, middle and lower course of the river. So as a reminder, you've got 3 courses of the river. The characteristics of the river change as you move further downstream, and you'll see that now as we go very briefly through these. So near the source of the river, it's quite a steep gradient. This gives the river a lot of energy, so it will erode the riverbed vertically, so I'm going to start to see some narrow valleys. My big landforms I'm going to start to see here is the formation of a waterfall. A waterfall is an erosional landform, so it's caused when the river flows over alternate layers of rock. It's then going to start to create a bit of a step as it erodes vertically. They get even more hydraulic action and abrasion, which is going to form that plunge pool that you can start to see forming here. The hard rock then is going to keep being undercut, so this soft rock is going to retreat even further backwards. And what I'm left with as my waterfall moves even further back upstream is a steep-sided gorge. In the middle course of the river, the gradient starts to get a bit gentle. The river starts to have a little bit less energy, moves more slowly. Therefore, it's going to erode laterally, so sideways. So here I'm going to get things like meanders and oxbow lakes. Remember, if you're explaining oxbow lakes, you must explain meanders first, because that's what has to happen first in the process. Remember, you're going to get processes like helicoidal flow, that zigzag movement of water further down the river. If you look here, I've put in 4 steps to the formation of meanders and oxbow lakes. So that helicoidal flow, that zigzag movement here of the water, we can start to see. Over time, that river's going to start to bounce a little bit off each bank, so the loops on this meander get even bigger. Then what will happen is that the neck on that meander here will break through, so it creates me a brand new river channel, and it cuts off that old bend of meander. Then I'm going to get deposition as the water slows down in this bend here, so it's going to cut itself off, and that's what causes me that oxbow lake. In the lower course of the river, it's obviously much wider, the river's flatter, and we're going to get more transportation here, might even see some deposition, and this is where I'm going to get my floodplains and levees. So you can see levees in the diagram. These happen when the river floods, so that material is deposited on the valley floor, normally closer to the banks. The closer I am to the river, the bigger the material, and the further I move on to that floodplain, the smaller. So it's going to start to build up natural levees on either side of the river. These are particularly good, so it means I might have more nutrient-rich soil. If I've got the river flooding either side, might also mean here that soil's of better quality. I might have flat land also then for building houses, so it might be good for development. So your example of a river that shows off all of these would be the River Tees. Again, the River Tees has got high force waterfall, which would be your example of a waterfall. It's got the Darlington meanders, so that would be your example of meanders. And the estuary is not too far then from Middlesbrough, so that's where you've got your mud flats as well. They're still managing it. They've got dams and reservoirs in the upper course to try and control some of the flow. They're trying to get some better warning systems. You might argue that towns like Middlesbrough are economically and socially important if you've got houses that are located there on the floodplains but also close to the estuary for things like shipping and trade. A brief reminder about hydrographs, everyone's favourite graph to do with rivers, I'm sure. As a reminder here, river discharge is the volume of water that you've got in the river. Anything above base flow is flooding, as base flow is the normal level of water in the river. This graph will show you with the red bars the amount of precipitation that's fallen. The line is obviously tracking the amount of water that you then have within the river. You might be asked to describe what the area might be like. I'd suggest if you've got a high graph like this one here, this might be in an urban area, this might be at the bottom of a slope, so you'd have high levels of surface runoff. If I was looking for a rural area, I think the graph would have a shape like this red line that I've drawn on here, or perhaps this might be in an area that hasn't got too much of a gradient, i.e. relatively flat land. I've added on some of those key terms for you. So lag time is the time taken between peak rainfall and peak discharge. Here is your rising limb, and there is your falling limb as well. Just check, are you able to explain a couple of physical and human causes of flooding? So for physical, you might have heavy rainfall, you might have relief, geology. Human might be things like land use, farming, for example. Any of those, but again, just check, can you name it and explain it? Nearly at the end. So now you've got river management, hard versus soft engineering again. I won't explain what those are because I've done it again in coasts. But can you name and explain some of these methods? So things like afforestation, so planting trees to try and soak up rainwater and try and increase interception. Managed flooding, so that areas flood naturally. You might use hard engineering, so straighten some of the channel. You might deepen or widen the river, so dredging, so it can increase capacity, therefore reduce the risk of a flood. And so last but not least, your final case study with Boscastle. So Boscastle's in Cornwall, as a reminder. Here they had 1,400 million litres of water fall in just 2 hours. Hence they had huge amounts of flooding. For management here, they've tried to sort of lower the bed by an average of 0.75 metres, widen the channel, try and increase capacity of the river. They've built some embankments, again to try and protect some of the towns and cities. They've done floodplain zoning, so they've moved the car park further back from the river. Again, the issue with this one then might be that it's cost them quite a lot, so £4.6 million. It's more expensive to keep doing this. They've had to make huge insurance claims then because of the flooding last time. So again, just check, can you evaluate and weigh up exactly what you've got happening here? Is it beneficial? Has it actually made an impact? So I hope that's helped talk you through everything that there is on paper 1. As ever, if you've got any questions, come and see a member of the geography department. But I wish you the very best.